Today I'm going to teach you how to name hydrocarbons. If you think of the prefix hydro, you're probably thinking water. And of course, water is made up of hydrogen and oxygen and then carbon. So hydrocarbon means these are compounds that are made of mostly carbon, hydrogen. You're going to have some oxygens thrown in there and a couple of other elements for the more difficult ones. Hydrocarbons, I mentioned in our last lesson, are the compounds that make up living organisms. These are the most of the molecules in your body. Those of you who are going into a medical related field will need to take several classes on organic chemistry, and organic chemistry is just the study of hydrocarbons. So to do these, you are going to have to know some prefixes. Unfortunately, these first 5 prefixes are different than the prefixes that you learned for inorganic nomenclature, your mono, di, tri, and so on. So you're going to need to study these and memorize these and know these well. Thankfully, the last half are the same. And the reason for this difference is chemists typically either work with and study inorganic compounds or organic compounds, the chemicals in living organisms. And so very early on, chemists split into one of 2 fields and then unfortunately don't communicate with each other as much as we probably should. And so the nomenclature, the naming and writing formulas is a little different between the 2 groups. You'll need to understand one other thing before we get into the specifics. Let's look at some Lewis structures for carbon, hydrogen, nitrogen, oxygen. If you remember from probably 9th grade or your Chemistry 1 class, this is your basic, very simplistic Lewis structure of carbon. Carbon had 4 valence electrons, and we're using a dot to represent each valence electron. You spread them out around the atom, blah, 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 blah. So remember, the carbon can be stable by either losing all 4 of these or gaining 4 more. So if you look, we've got a spot to gain right there, gain right there, gain right there, and gain right there. So carbon can gain 4 electrons, and it can do that by sharing 4 electrons with another element, and therefore we say it can form 4 bonds. Okay? If we study oxygen's simplistic Lewis structure, oxygen has 6 valence electrons. So if we look, oxygen could gain or share an electron right there and right there. So we say the oxygen can form 2 bonds. Let's look at nitrogen. I'm going to do nitrogen over here. Nitrogen has 5 valence electrons. So if you look, we see nitrogen can form 1, 2, 3 bonds. Okay, I do not yet expect you to be able to draw Lewis structures. I'm going to teach you how to do that very soon. But what I do want you to take from this is that carbon can form 4 bonds. Oxygen can form 2 bonds, and nitrogen can form 3 bonds. Okay, so you're going to need to remember that information, and then your hydrogen will only form 1 bond. Okay, with that background information, we are going to now start naming and writing formulas. Your hydrocarbons are divided into 3 main groups. They're either called an alkane, an alkene, or an alkyne. So let's start with these alkanes. I like to use colors to explain this lesson, to explain this concept. So if you would at this point pause the video and get out either colored pencils or highlighters or crayons or whatever you would like to use. Okay, so like I said, there are 3 different classifications of hydrocarbons that we're going to study. The first is called an alkane, and the way we do these is listed in number 2 right here. So I'm going to draw out an example, and I'd like for you to sketch this in your notes as well. Let's draw 3 carbons. They're going to be bonded to each other, and then each carbon is going to have a total of 4 bonds coming off of it. So I'm going to fill everything with hydrogens. Remembering that carbon can form 4 bonds, so you've got to have 4 dashes coming off of each and every carbon. When I look between the carbons right here, I see single bonds, and I'm only focusing on the bonds between the carbons, nowhere else in the molecule. If you see single bonds between those molecules, that's how you know, between those carbons, that's how you know that this hydrocarbon is an alkane. There will be single bonds between the carbons. When that happens, it's called a saturated molecule. If I tell you a sponge is saturated with water, that means that the sponge cannot hold any more water. It's full. And the same thing for these. Each and every carbon is bonded to 4 different elements, and therefore it is full. The carbons are full of other elements. They can't hold any more atoms, any other elements. There are no gaps that I see in the molecule. Everywhere you look, it's full of hydrogens. Okay? So if you've got an alkane, it is a saturated hydrocarbon. And once again, I can identify it as an alkene because there will be single bonds between the carbons, and I'm only looking between the carbons. Now, we get a little lazy. I think you would agree that writing out all those hydrogens is going to be a pain, especially as the molecules get bigger and bigger. So next, I'd like to show you a little shortcut. What we are going to do is I'm going to draw a dash, and because these things are going to have so many hydrogens, if you don't see anything up here on the other end of the dash, we are going to assume, we are going to have the understanding that if you don't write anything in there, that it represents hydrogen. So what I'm going to do is just draw that dash. That means there's a hydrogen, another hydrogen, another hydrogen, 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 hydrogen. Now, what I've just drawn is called the structural formula, meaning I have drawn out a diagram that shows you the structure that hopefully will help you visualize a little bit of the 3-dimensional structure. We can also write this in a simpler form. I can write a C to represent, I'm going to start with this carbon right here on the left. So I'm writing a C to represent that carbon on the left. And then I'm going to say it has 3 hydrogens coming off of it. And then that is bonded to another carbon that has 2 hydrogens coming off of it. And then the final carbon that has 3 hydrogens coming off of it. Or I can lump all of that together and say there are a total of 3 hydrogens and a total of 3 carbons and 8 hydrogens in this molecule. So what I've drawn right here is often called the molecular formula. Now, I do not care that you memorize structural formula and molecular formula. I am not going to ask you for the definition of each. But some of your practice problems will say, draw the structural formula or write the molecular formula. So I just want you to know exactly what they're asking you for when you see that in the practice. Okay, so then how would we name this thing? Because that was the whole point of doing this, drawing and writing names, right? So I have given you this structure. How would you take what I've given you and name it? So I am going to focus, look at this one right here. I think that one is going to be the easiest one to use. The first thing we need to do, let's go back up here to our how-to, number 2. Well, the first thing we need to do is count the number of carbons in the longest chain. And guys, instead of counting, I actually circle them. So take your pen or pencil and circle the carbons, only the carbons, And you're going to circle until you don't want to pick up your pencil. Circle the longest number of carbons that you can, the greatest number of carbons as you can without picking up your pencil. In this case, it was 3 carbons. So next in this number 2 up here, I tell you to use the appropriate prefix. The prefix that goes with 3 is prop. So how many carbons do you have in the longest chain? Write down the prefix that goes with that number of carbons. And then because I only have, if you'll focus right here, I'm going to shift colors, hopefully so you can see a little better. If you focus between your carbons, I only see single bonds. That means it is an alkane. So I am going to use the suffix, the ending ane, because it's an alkane. Okay, right there in your notes. So I am going to call this molecule propane. All right, so this, what I've drawn, is called propane. That would be how you name that structure that I have drawn. That would be the correct name. Okay, let's do one more just to make sure you've got it. If you'll draw out this molecule for me, draw it just like I am. Notice I'm filling in, giving each and every carbon a total of 4 bonds. Okay, so I'm right here on number 2. I need to figure out and count the greatest number of carbons that are hooked together, the carbons in the longest chain. So I'm going to start on the left-hand side. I'm going to circle the carbons, the greatest number of carbons that I can circle without picking up my pen. Count them, 1, 2, 3, 4, 5. Use the prefix, that means 5. Pent. Look at the bonds between each carbon. I only see single bonds, therefore this is classified as an alkane, so I use the ending ane. So this would be called pentane. I have drawn the structural formula for you. If they asked you for the molecular formula, you could either write CH3, CH2, 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 CH3, or you could put all of that together if you prefer, and you could say C5H, in this case it would be 12. Very good. Okay, so let's add on a little bit more information. What do you do if you have something called a side chain? So I give you the little list of how to do these down here. These are your bullets. Let's start with an example molecule. So sketch in your notes one that looks exactly like what I'm about to draw. Okay, pause the video to get that in your notes. Now, when we're ready, I am going to start this the same way I did the last one. I want to determine the greatest number of carbons that are hooked together, the longest chain of carbons. So please watch. I've got several options. Don't draw this in your notes, just watch me. So I've got this option, in which case I would have 1, 2, 3 carbons hooked together. Remember, you're looking for your greatest number of carbons that you can circle without picking up your pencil or pen. I could do this, in which case I would have 5, or I could do this, in which case I could have 5. So I could either do this one, or I could do, this one. Most students prefer to work these with a circle that just goes straight across your paper. So let's all use this one. But I do want to say, if you had instead left this carbon on the left out and circled this top one instead, you're going to get the exact same answer because both of those had 5 carbons in the longest chain. Okay, I'm going to do this in a little different order than your notes. I always start by naming my base chain. So I'm doing this 4th bullet down here first. I have 1, 2, 3, 4, 5 carbons in my longest chain. The prefix for 5 is pent. I look between the carbons here, 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 here. I only see single bonds. That means this is an alkane. So I use the ending ane. Next, I'm going to go back up to this bullet. I need to number the side chain from the closest end of the molecule. Okay, do you see how you have this little guy up here hanging out? He was not part of your longest chain. He was not part of your base chain, and therefore he is called a side chain. A side chain is a group of carbons that comes off of that base chain. So I need to determine which carbon he is coming off of. Now, you're either going to start numbering from this side, the left side, or the right side. To determine which, I want you to think about dividing your longest chain in half, right down the middle. Which end, the left or the right, is this side chain closest to? In this case, our answer would be the left-hand side. So I'm going to start numbering the carbons in my base chain from, in this case, the left-hand side. You will always start numbering from the closest end of the molecule. So I'm going to call this carbon 1, 2, 3, 4, and 5. So my little side chain is coming off of carbon 2. So I'm going to write a 2. Leave yourself some space. That 2 tells me the side chain comes off of carbon 2 of the base chain. Next, I'm down here. I need to communicate how many carbons are in the side chain, the number of carbons in that side chain. In this case, I have 1 carbon in that side chain. The prefix for 1 is meth. I need to communicate that this is part of the side chain, not the base. So the way I do that is add the ending YL. Anytime you see something that ends in YL, that means it's a side chain. So the proper name of this one would be 2-methylpentane. What do you do if you have more than one side chain present in that molecule? Okay, so get this next example sketched into your notes. Make sure yours looks as close to mine as possible. And now I need to make sure that each and every carbon has a total of 4 dashes coming off of it. Meaning each and every carbon, even these little side chains down here, has to have 4 bonds. Okay, pause the video if you need to have more time to get that sketched into your notes. Okay, so I'm going to start this the same as usual. I'm going to determine the greatest number of carbons that are hooked together. The longest chain that you can circle without picking up your pen or pencil. So don't write this down. Let's just take a minute to look at the possibilities. So I could do this, in which case if you count them up, I'd have 1, 2, 3, 4, 5, 6, right? Okay. I could also do this, in which case I would have 1, 2, 3, 4, 5, 6. So that's identical to the last one. So far my greatest is 6, and it wouldn't matter which of those 2 I circled, I would get the exact same answer. I could do this, in which case I would have 1, 2, 3, 4, 5. Okay, nope, not that one. And then I could do this. That would be 3. That's a great big no. I could do this. That would be 4. That's a great big no. So it looks like my longest chain has 6. So I am going to go back and circle this one. Okay, circle that one for me. And that's the one that we are all going to use. Once again, it wouldn't matter if you had circled this one and left this one off. As long as your base chain has the greatest number of carbons, you're still going to get the same answer as I do. Okay, so I'm going to start by naming my base chain right here in your bullet point. This has 6 carbons, so I'm going to use the prefix hex for 6. When I look between my carbons, I only see single bonds between my carbons, and I'm only looking at the carbons in my base chain. I don't have to look at the side chains. So just the carbons that you have circled. What kind of bond do you see in between the carbons? In this case, single, so it's an alkane, so I use the ending ANE. Now, I need to deal with my side chains. So I've got a side chain right here, and I've got a side chain right here. So I need to start by determining what carbons are those side chains coming off of. Think of taking this molecule and dividing it right down the middle. In this case, it'd be right here. Which end of the molecule does it look like the side chains are closest to? The left-hand side or the right-hand side? In this case, it's the left-hand side, okay? It looks like everything's closer to, kind of shifted over to the left side. So I'm going to start numbering the carbons in my base chain from the left-hand side, the side that those are closest to. That'd be carbon 1, 2, 3, 4, 5, and 6. So I have a side chain coming off of carbon 2, and I have a side chain coming off of carbon 4. Now I need to name those side chains. This one right here, they're 2 completely separate side chains, so I need to name them separately. This one on the left has 1 carbon in the side chain, so the prefix for 1 is meth. Right? Use a prefix to tell me how many carbons are in the side chain, and then I'm right here because it's a side chain, I'm going to use the ending YL. The one on the right also has 1 carbon, so it's also a methyl group. Now, do you see how these 2 are the same? So instead of writing 2-methyl, 4-methyl, I am going to use the prefix di right here in your notes. You can use the prefix di or tri if you have more than one of the exact same side chain. So in this case, since I have 2 methyl groups, I'm going to say I have 2,4-dimethyl, meaning I have 2, that prefix di means I have 2 methyl groups, 1 coming off of carbon 2 and 1 coming off of carbon 4. Okay, very good. If you end up with completely different side chains, you will place those in alphabetical order. So right here, this little di and tri will be used if you have side chains with the same prefix, 2 methyls, 2 ethyls, 2 props, or alphabetical order applies if you have side chains with different prefixes. So let's say I had a methyl group, let's say it was coming off of carbon 2, and let's say I had an ethyl group and it was coming off of carbon 3. I would put those in alphabetical order based on the prefix. So I would call that 3-ethyl, 2-methyl, and then whatever your base chain is called. Let's do another example together. Try and make your molecule look as close to mine as possible. 3, 4, 5. Let's go 6 carbons across. And then right here I want to do 2 carbons. And right up here, I want to do 2 carbons. And then I'm going to add hydrogens to make sure, and I'm going to add enough hydrogens to make sure that each and every carbon has a total of 4 bonds, even if it doesn't look like it's part of your base chain. Every carbon must have 4 dashes. It cannot have any more than 4. Okay, the first thing we need to do is identify our longest chain. So let's start with this one. So if I circle that one, I would have 1, 2, 3, 4, 5, 6. So that's 6 carbons. Okay, let's try another one. What if I did this? That would be 1, 2, 3, 4, 5, 6. That's identical to the one I just circled. You could choose either of those. Okay, how about if I did this? That would be 1, 2, 3, 4, 5, 6 again. Okay. All right, how about this one? Okay, if I do that, I have 1, 2, 3, 4, 5, 6, 7. Okay, so this is my longest chain. You have to use this one as the longest chain. If you use any of the others, it's incorrect. So my longest number of carbons hooked together, remember it doesn't have to be in a straight line, it can bend like this one right here. It's just the longest number that you can circle without picking up your pen or pencil. In this case has 7. The prefix for 7 is hept. Between the carbons that I have circled, I only see single bonds. That means this is an alkane, so I'm going to use the ending ANE. Now, I see 2 side chains. I see a side chain right there, and I see a side chain right there. So my first job is to determine which end of the molecule those are closest to. To me, it looks like they're closest to this side. Like if this has 7 carbons, I would cut the base chain in half right about here, right? Right on that carbon. So are they closer to this side of that half or this side of that line? And the answer is this side over here. So that means I am going to start numbering my carbons from this carbon right down here. So that'd be called carbon 1, 2, 3, 4, 5, 6, and 7. So this one is coming off of carbon 3, and this one is coming off of carbon 4. I'm going to move that 3 up a little higher. Now I need to name these side chains. This one coming off of carbon 3 has 1 carbon in it, so that's a meth group. And I'm going to use the ending YL to show it's not part of the base chain. This, though, has 2 carbons hooked together in this second side chain coming off of carbon 4. So that would be called an eth group, and I'm going to use the ending YL because it is a side chain. So I cannot use the prefix di or tri because these side chains are different. They have different prefixes. They have different numbers of carbons in the side chains. So the way I do it is I put them in alphabetical order based on the prefix. That one starts with E, this one starts with M, so I'm going to write the ethyl before the methyl. So I will call this 4-ethyl. The 4 has to stay with the ethyl because that tells me the ethyl group is coming off of carbon number 4. So you have to keep those together, and I don't care if there's a space or dash, or I don't care about any of that. Just keep those 2 together. And then I would write 3-methyl. So the correct name for this one would be 4-ethyl 3-methyl heptane. Okay, if you really understood those, then the rest are going to be fairly simple because all we're doing now is we're changing from an alkane to an alkene. Alkenes are hydrocarbons that are unsaturated, meaning there's going to be at least 1 double bond between the carbons in your base chain. Remember, we're only worried about the bonds between carbons in the base chain. So let's do an example of this one together. I'm going to draw in this. Now remember, each carbon can have 4 bonds, and it can only have 4 bonds. So on the carbon on the left, I am only going to add 2 dashes because that carbon already has 2 bonds right here. It shares 2 bonds with the carbon. So 1, 2, 3, 4. Let's look at that middle carbon. It already has 3 bonds. So I'm just going to add in 1 more hydrogen. And let me say, where you put your hydrogens doesn't really matter for now. You can put them up, down, coming off at the side, at an angle. I don't care. So just as long as you're drawing a dash somewhere on that carbon, it doesn't matter to me where it is right now. Now this carbon on the far right, it only has 1 bond, so it needs 3 hydrogens. So do you see how right down here on this part of the molecule, it looks empty. It looks like it's not full. It looks like you've got empty space. That's why this is called unsaturated. The hydrocarbon is not full of hydrogens. 2 hydrogens in this case. Could have been a hydrogen there and a hydrogen there, but they have been removed to change this to a double bond instead of a single bond. It's called a double bond because you see 2 dashes there. And it truly creates open space in 3 dimensions. If you've studied anything about nutrition, you've got your saturated fats and your unsaturated fats. Your saturated fats are typically considered more dangerous. They tend to clog your arteries more. Unsaturated fats tend to be a little safer to eat. And the reason for that is there are gaps in 3-dimensional space. There's empty space on those molecules that allow, if those fats accumulate, say in your arteries, it allows the blood to continue to flow a little better than the saturated fats because there is truly empty space available for that blood to flow through. Okay, so how would I name these? Okay, so you still have to start with your base chain. So this one's simple. Your base chain contains 3 carbons, so I'm using prop. But now because of this double bond that I see right here, I'm going to change the ending. It's an alkene because there's a double bond present between the carbons. So instead of propane, I call it propene. Okay, I have to be told where that double bond is. Just like you had to label where the side chains were, you have to label where the double bond is located. So we're going to number from the closest end of the molecule. So to me, that double bond looks like it's closer to this left-hand side of the molecule than the right-hand side. So I'm going to number this carbon 1, 2, 3. And we are going to label the carbon that the double bond starts on. And we're going to use a number right before the name of the base chain to tell us. So I would call this 1-propene. So your final answer for this one would be 1-propene. Okay, if you have a double bond and side chains, I tell you in your notes right here that the double bond takes priority over side chains when you're trying to determine which is the closest end of the molecule. Let's do an example of that. If you would please sketch this one in your notes and once again make it look just like mine. Okay, let's go through. Make sure every carbon has a total of 4 dashes. It has to have 4 and it cannot have more than 4. Okay, watch right here. I have a lot of students do this. That is incorrect because if you do that, this carbon right here would have 1, 2, 3, 4, 5 bonds. So you can't add 2 dashes to that carbon, just 1. It already has 3 bonds, it just needs 1 more hydrogen. I don't care if you put it on top or bottom. And then this carbon on the left already has 2, so I need to give it 2 more hydrogens. Okay, let's identify our base chain. If I circle this, my longest chain would have 4. If I circle this, my longest chain would have 4. If I circle this, my longest chain would have 3, so that one's not going to work. So I'm going to use this as my base chain. Prefix for 4 is bute. I see a double bond between 2 carbons in that base chain. That means this is an alkene instead of an alkane, so I'm going to call it butene instead of butane. Now I need to label where that double bond is in the molecule. I see a side chain right here that I'm going to have to deal with. It looks like halfway the molecule would be right about here. So which end does everything look like it's closest to? And remember, your double bonds take precedence over your side chains. So clearly the double bond is closest to the left-hand side of the molecule. So I'm going to call this carbon 1, 2, 3, and 4. So the double bond starts on carbon 1, so I'm going to call it 1-butene. I'm going to put that 1 right before the word butene. I need to name this side chain. It's coming off of carbon 3. The side chain has 1 carbon, so I use the prefix meth, and because it's a side chain, I use the ending YL. So this would be called 3-methyl-1-butene. Okay, very good. So then let's cover our alkynes. Once again, if you understood alkenes and alkenes, this is super easy. So sketch in this molecule for me. Now I need to make sure everything has 4 bonds. Every carbon has 4 bonds. This carbon right here already has 3, so I'm just going to add 1 more dash, meaning it will only be bonded to 1 hydrogen because there's 3 bonds between those carbons. Okay? This second carbon, or third, whichever end you're counting from, already has 4 bonds, so I'm not going to add any hydrogens to it. This carbon needs 2 hydrogens, this carbon needs 3. If you use the wrong number of dashes, it is wrong. So take your time and count. Make sure every carbon has 4 dashes and only 4. Okay, right there is my base chain. Longest chain has 4 carbons, so I'm using the prefix bute. I see a triple bond between these carbons in the base chain, so therefore it is called an alkyne. So I'm going to use the ending YNE. So this would be butine. If there was a double bond in there, it would be butene. If there was a single bond, it would be butane. But because I see a triple bond, this would be called butine. You need to tell me where that triple bond is. Looks like it's closest to this side of the molecule, so that's carbon 1, 2, 3, 4. It's starting on carbon 1, so I would call this 1-butine. And that is how you would properly name this molecule. Now we can put all kinds of other things on these base chains as well, in addition to your side chains or your double, triple bonds in the base chain. So the extra stuff that we put on are called functional groups. You need to be responsible, you need to be aware of and know several functional groups. The first is an alcohol or a hydroxyl group. Hydroxyl should make you think of your polyatomic ion hydroxide, OH with a -1 charge. It doesn't have that -1 charge in this case because it's bonded to something, but it is the OH, okay? So for these, you will have an OH bonded to that base chain, coming off of that base chain. It will look kind of like a side chain, but instead of being a side chain of just carbons and hydrogens, it's going to have an O bonded to an H. Now, I've abbreviated it this way in your notes, but I would like for you to sketch it out in a little bit more detail. If you do it this way, it's going to really help you in a couple of lessons. The oxygen will be bonded to the hydrogen. The oxygen will have 2 lone pairs of electrons that are not involved in the bond, and then this oxygen will be bonded to a carbon over here. Okay, now typically that carbon is bonded to other stuff. So sometimes you're going to see this written as an R, meaning the rest of the molecule. So the OH will be bonded to carbons and whatever else those carbons are bonded to over here. Okay, let's do an example of naming these. So if I was to draw out this structure, here's my lone pairs. Okay, I'm still going to circle my base chain of carbons. Your longest chain of carbons, in this case, has 3. Prefix for 3 is prop. Look between your carbons. I see single bonds, so it is an alkane. So I'm going to add the ending ane. I don't see any side chains or any double or triple bonds that I need to worry about. So the only issue I have is this little guy right here. I have to name him. I tell you, you name him by replacing the final E in the name with OL because it is an alcohol group. So I'm going to take off this E and change it to OL. So I would call this propanol. Now we have to do one more thing. This OH could be anywhere on the molecule. So just like you had to tell me what carbon the side chain is coming off of or the double or triple bond, you have to tell me the carbon that this one is coming off of. It looks like everything's closest to the right-hand side of the molecule. So I'm going to label this carbon 1, this carbon 2, this carbon 3. So I'm going to call this 1-propanol, telling me we have an all group, meaning an alcohol group or a hydroxyl group, which is OH, coming off of 3 carbons, and it's coming off of carbon number 1 of those 3. Okay, your next functional group is something called an aldehyde. So an aldehyde is going to have a double bonded oxygen, and that double bonded oxygen is going to be on the first or the last carbon. Let's draw in an example of this one. Okay, be careful here. Remember, carbon currently has 3 bonds, so I'm going to just add 1 hydrogen there. This carbon needs 2 more hydrogens, and this carbon needs 3 hydrogens. Okay, I want to do one more thing to this one as well. This oxygen has 2 lone pairs on it, and I don't care where you draw them. I'm going to kind of draw them spread out. So you've got the double bond. The oxygen will be bonded to the rest of the molecule, and then this oxygen itself has 2 lone pairs. So do you remember me telling you at the very beginning of this lesson that carbon typically forms 4 bonds? Your oxygen will only form 2. It's because you've got these 2 electrons, right, 2 lone pairs of electrons right there. And I would like for you to draw those in. If you do, it's going to make things in a couple of days much easier. Okay, let's draw in or circle our longest chain. 3 carbons, single bonds between those, so it's propane. Remember, you're only focused on the single, double, triple bonds of what you've circled in the base chain. I'm not worried about this one out here. You determine whether it's an alkane, alkene, or an alkyne based on what you've circled for that base chain, based on what's inside that circle, not outside. So to name this one, I need to replace the last E with AL because this is an aldehyde. So I'm going to take off this E and change it to AL. And then it's good to tell me where it is. Looks like it's closest to this end of the molecule. So that's carbon 1, 2, 3. So I'm going to call this 1-propanol. Okay. Your next functional group is something called a ketone. It is also a double bonded oxygen. Let's draw out that oxygen with your 2 lone pairs again, and it will be bonded to the rest of the molecule again, whatever else is there. And it's going to be on a carbon in the middle. Now, when I say middle, it does not have to be dead center of the molecule. What I mean there is it's not the first or the last carbon. It can be any of the other carbons other than the first or last. So middle does not mean dead center. Let's show an example of that one. I'm going to draw in my lone pairs. So the carbon over here on the right only has one bond, so it needs 3 hydrogens. This carbon already has 4 bonds, so I'm not going to put any hydrogens on it. This one needs 2, this one needs 3. Start by circling your base chain. I see single bonds between these carbons, so it's an alkane. So 4 carbons, prefix is butane. Now I need to deal with my functional group, this one right here. I tell you, you name it by replacing the E with -one because this is a ketone. So I'm going to cross off this last E in butane and change it to ONE. And once again, you need to tell me where it is on the molecule. So this looks like about the middle. It looks to me like it's closer to this side. So I'm going to start with the right-hand carbon when I'm numbering 1, 2, 3, 4. So that's coming off of the double bonded oxygen. The ketone is coming off of carbon 2. So this would be called 2-butanone. And that's my proper name for this substance. Now, guys, your ketones and your aldehydes look very similar. They're both a double bonded oxygen. It's just where it is in the middle. So to help you remember that, you can remember A comes at the beginning of the alphabet. K comes in the middle of the alphabet. Or if that doesn't work for you, you put a key in the middle of a lock when you're opening a door or whatever. Next functional group is something called a carboxylic acid. So for this one, you're going to have the rest of the molecule, whatever else that is. So at the end of the molecule, you're going to have a carbon. And then that carbon is going to be bonded to a double bonded oxygen and a single bonded oxygen that's bonded to a hydrogen. Let's go back and fill in our lone pairs. This oxygen has 2 lone pairs and this oxygen has 2 lone pairs. So the functional group is this right here. It's a, I call it a COOH group, C-O-O-H, okay? It will always be on the first or last carbon because there's no other way it can bond because this carbon right here has already used up 1, 2, 3 bonds, so it can only bond to one other thing. Let's do an example of this one. Okay, I'm going to draw in my lone pairs on my oxygens. Okay, so to name it, circle your longest, oh, I'm sorry, I forgot my hydrogens. Let's go back and fix everything. This carbon is good. The one on the right, it already has 4 bonds. This one needs 2 hydrogens. This one needs 3 hydrogens. Okay, now let's circle our longest chain of carbons, and I will include the carbon of the COOH group, of the carboxylic acid, in my longest chain. Between these, I see single bonds, so it is an alkane instead of an alkene or an alkyne. I see 3 carbons that I've circled, so my prefix is prop, and because it's an alkene, it would be propane. So I'm going to replace the very last E with oic acid. So this one would be called propanoic acid. And then if you number from this end, 1, 2, 3, that functional group is coming off of carbon 1. So 1-propanoic acid would be the correct name. Okay, very good. So then, ladies and gentlemen, we have nitrogens that we can add to these. You are not going to be required to name these. All I want you to be able to do is identify these as amines. So if I draw a hydrocarbon for you and ask you which of the following is an amine, what you're looking for is which hydrocarbon contains nitrogen. And then I want you to determine or be able to tell me if it is a primary amine, secondary amine, or tertiary amine. Let me show you what those mean. So for your primary amines, you will have a nitrogen bonded to one carbon. One meaning primary. It will look something like this. So I'm going to have the rest of the molecule, I'm going to draw it as a squiggle, or you can write an R. Here's a carbon. That carbon will be bonded to a nitrogen. That nitrogen has one lone pair of an electron. There will be a hydrogen right here and a hydrogen right here. So you can draw in your H's, or if you prefer to the shortcut and just draw the dash, that rule still applies. If you see a dash, it just means there's a hydrogen at the end. This carbon would probably have two hydrogens coming off of it, just based on whatever else it was bonded to. So do you see how this nitrogen is bonded to one carbon? That would be called a primary amine. Secondary amine, your nitrogen is bonded to two carbons. So that would look something like this. You would have a carbon, then your nitrogen, and the nitrogen would be bonded to a carbon that's hooked to some other part. We would still have your lone pair on your nitrogen, and that nitrogen would be bonded to one hydrogen. Okay, and these hydrogens would probably have these carbons would probably have two hydrogens on each of those, but once again, that would just be based on what they're bonded to. Now, a tertiary amine, the nitrogen will be bonded to three carbons. So it's going to look like this. Here's the rest of the molecule, rest of the molecule, rest of the molecule, and nitrogen would have a lone pair of electrons. When you're naming these, you would use the prefix amino. Once again, I do not expect you to be given this drawing and name it, but if I give you a name, you should be able to identify that it has a nitrogen present in the molecule. Amino acids from biology, if you remember those structures, they have nitrogens. And it's called an amino acid because it's actually a combination of an amine and a carboxylic acid functional group. So it's those two kind of hooked together. Okay, you need to know how to name hydrocarbons if we have a halogen present. So for example, let's say I have 3 carbons, and on this side, I have a bromine hooked to the carbon instead of a hydrogen. So let's start by identifying our longest chain right there. Between those carbons, I see single bonds, so that would be called propane. Okay, to name these, you're going to use the prefix chloro, bromo, fluoro. Okay? I think that pretty much does it. I think those are the only 3 that you're going to see. If you saw iodine, it would be iodo, but I won't give you that one. That one sounds so strange. So this, because you see a bromine present right here, this would be called bromopropane, and you have to tell me where that bromine group is. In this case, you would number from the left-hand side of the base chain, so it would be coming off of carbon 1, so the proper name would be 1-bromopropane. So I don't expect you to be able to name amines, but I do expect you to be able to name halogens. Esters and ethers. These are like your amines. I expect you to identify them, but you do not have to name them. So I will give you a molecule drawn out, and you will tell me whether there is an ester or an ether present in that molecule. So I'm drawing in these squiggle lines. That just means bonded to whatever's on the rest of the molecule. I'm going to add my lone pairs to my oxygens. Those are going to be important in a few days. So your ester group, you will have a carbon that's double bonded to one oxygen and single bonded to another oxygen, which is then single bonded to a carbon. So what I've shown you in red is your ester group. Your ether looks just a little different. If you watch this one, this would be the rest of the molecule. I've drawn in 2 hydrogens on each of your carbons. Once again, that would just depend on what they're bonded to. Do you see on this one, you just have this oxygen between the 2 carbons. You do not have this double bonded oxygen sticking up here. Okay, so I remember that the double bonded oxygen is present for this one because this word looks like Easter to me. And when I look at this double bonded oxygen, I think of that double bond like Easter bunny ears. So that's how I remember your Easter. It's actually called an ester, but you can remember it even if you can't pronounce it. You can remember it. Easter bunny ears, the double bond between the carbon and the oxygen looks like those Easter bunny ears. Very good. The last thing I want to talk to you about in this lesson is something called isomers. So isomers are going to be hydrocarbons that have the exact same formula, but different three-dimensional structures. Let me show you a picture of what I mean by that. If you look at these 2 structures, so this black dot represents carbon. So I've got a carbon and another carbon right here. That carbon is bonded to something down here, and then you've got something else up here and up here. You see 2 springs. That represents 2 bonds, so that would be a double bond. So this would be an alkene. Now, if you study this one down here, it has the exact same thing. I see the 2 carbons, I see the 2 white spheres, I see the 2 green spheres, I see the double bond. It's got the exact same thing. This would have 2 carbons. I'm going to call that green element G, so it would be C2, G2. I'm going to call the white sphere W. This one would be C2, G2, W2 as well. So they have the exact same molecular formula, right? But if you look at these 2 in 3-dimensional space, they look very different. And that difference is important. In this case, the 2 white spheres are both on the bottom. In this case, 1 white sphere is coming off of the top and 1 white sphere is coming off of the bottom. So while they have the same formula, they have different 3-dimensional structures in space, and that is called an isomer. Isomers are very, very important, especially in pharmaceuticals. In the 1960s, there was a drug developed called thalidomide. It was given to pregnant women to prevent morning sickness. There were 2 isomers of the chemical. And at that time, chemists and the people manufacturing the drug didn't pay attention to those isomers. One of the compounds worked great. The other one caused severe birth defects. I mean, just horrendous birth defects, like children were born, without legs. Children were born with arms coming out of their stomachs. The drug, once again, was called thalidomide. If you're interested in that, you can just look that up on the internet. About 50% of the children who were born passed away, and it affected thousands, like tens of thousands of children survived but had serious birth defects. So isomers are important. It matters in your body. The way the chemical reacts with your body matters if the part of the molecule that you're talking about is on the top or the bottom. Now, there are many, many different forms of isomers. We are just going to cover just a couple of very basic isomers, okay? The first is something called a cis versus a trans isomer. So that's the example that I just showed you. Let's sketch this in your notes. Let's say we have a carbon double bonded to a carbon, and let's say I have a carbon coming off of this side. I have a carbon coming off of this side. Down here I have a hydrogen, and down here I have a hydrogen. Or I could draw that with a carbon with your 3 hydrogens coming off the top, and a carbon with the 3 hydrogens coming off the bottom, and a hydrogen coming off the top, and a hydrogen coming off the bottom. So are things on the top and bottom, or are things across from each other? One on the top, one on the bottom. Do you see how up here it looks like the carbons are on the same side? Down here it looks like the carbons are on opposite sides, across from each other. So the cis isomer is the one in which the two are on the same side, the one in which the two are closer to each other. So this would be your cis isomer. The trans isomer are the ones in which they are farther apart, when they are across from each other. So this would be the trans isomer. And you would just use the little prefix cis or trans when you're naming these. I do not expect you to be able to give me the complete name of isomers. I will draw the structures and I will ask you to identify which of these is the cis isomer and which of these is the trans isomer, okay? Now, I remember this vocabulary because to me this makes me think of sisters. Sisters tend to be close. They tend to be on the same side. They tend to have each other's backs and therefore be on the same side of an argument or whatever, okay? That's assuming you like your sister if you have a sister. Trans means across, like transgender, cross genders. So right here, do you see how these carbons are across the molecule from each other? One on top, one on bottom. Another type of isomer that I expect you to know is something called iso versus N. So let me draw in two, and then we'll talk about them. Let's draw in, let me switch to black since it's what I've been using for your base chains. Let's draw in 4 carbons. We're just going to keep it very simple, and let's make it an alkane with no functional groups, no side chains. Okay, if I draw that formula is going to be C4H10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Now I can draw that a different way where I still have 4 carbons and 10 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. My formula is still C4H10, but this would have a completely different name. Do you see how right here your base chain has 4, so you would call this butane. This one right here, you have 3, so you would call that propane, and you have a side chain coming off of it. That would be called 2-methyl propane. So while the formulas are the same, the names are different. And that's a good way to be confident that you've drawn an isomer. If you write out the name, is it different? Do you have a different name even though they both have the exact same molecular formula? So for these, let me clear this out so that we can just focus on just the structural formula, just those right there. So if you look at these two, If you look at these two, the one on the left, the carbons are all in a straight line, or the carbons are all in my base chain when I circle my base chain. If the carbons that you're looking at are all in the straight line, that is your N isomer. So I would label this N-butane, if you ever see that. I do not expect you to name these. Once again, I will draw out the two and ask you which is an N isomer and which is an iso isomer. The prefix iso means that you've got a side chain present. So this one would be your iso isomer. You've heard of isopropyl alcohol. Iso meaning that there is a carbon coming off of your base chain. And in that case, the base chain has 3, because you hear prop, the base chain has 3 carbons. Okay, let me show you these pictures one more time, and let's go through and make sure you understand that. Do you see on this top picture, the greens are both on top, the whites are both on bottom. So this one, you've got a white on top, a white on bottom, or a green on top, a green on bottom. They are across the molecule from each other. So this would be your cis isomer. This would be your trans. Okay. I've also drawn out or made molecules of those N and iso. So let's look at these. Do you see how, let me scroll up just a little bit so you can see the top of that picture. There we go, that's better. Do you see how on this top picture, you've got these 3 carbons right here hooked together, and then you've got this one side chain up here. So we still have a total of 4 carbons, but one of them is a side chain. Down here, they're all hooked in the same line. So this would be your N isomer. This is your iso isomer. And then, guys, I've done that, taken pictures of those same molecules, but just from a different angle, from the top instead of the side. So do you see how it looks like this one right here? You've got something coming up out of the page at you, and this one, they're just all in a straight line. So this would be N, this would be your iso. I have these models available if you are more of a tactile learner and you learn better by touching, feeling, moving stuff around. I've got these available. Just let me know if you need them, and you can hold them, feel them, kind of play with them. But I just need to know so that I can sanitize them, get them good and clean before we swap around and anybody shares. Okay, a couple other things we need to cover before we wrap up this unit. I do expect you to be able to recognize something called a cyclic or a ring hydrocarbon, and I just want you to be able to identify one. Some of these hydrocarbons get so long that your carbons can bend and loop back around and bond to the first carbon. So they end up forming these rings, these circles, okay? The most common one is something called benzene. So benzene looks like this. Okay, now I'm going to go back, add my double bonds. Each carbon currently has 3 bonds, so I'm going to have to add 1 hydrogen on each of them. So that is benzene. It has 6 carbons. It has double bonds alternating between carbons, and every carbon has 1 hydrogen coming off of it. And guys, we get a little lazy drawing all of that out. So because it has 6 carbons, this is typically drawn as a hexagon. So if you see a hexagon drawn for a hydrocarbon, and then instead of drawing out those double bonds, we just draw a circle in here saying you've got a double bond alternating between each and every other carbon in the molecule. So I just expect you to be able to recognize that these ringed hydrocarbons exist. I don't expect you to be able to draw these, and I do not expect you to be able to name these other than identifying benzene. And I would like for you to know the shortcut method of drawing benzene, because when you get to chemistry in college, and especially if you have to take organic chemistry, you're going to see benzene over and over and over. So it'd be good for you to be familiar with it. Okay, we need to do one last thing for this unit, and in terms of isomers, it is the most important thing that you will do. It is probably how you are going to be tested on isomers on the AP exam. It is definitely how you will be tested on isomers for my test. You know, labeling the cis-trans stuff, that's an easy multiple choice question, but you are going to also have to be able to draw out some isomers. So let's do some examples of that. So let's look at this part of your notes right here, right under your definition of isomer. Let's say I have the formula C3H6O. So let's try and draw that. That means I have 3 carbons. Okay, I have to have an O in there somewhere. Now, you've got several choices. You could try and put a double bonded oxygen on, or we could put a single bonded oxygen and then bond it to an H. So think about your functional groups that contain oxygen as either your alcohol, your OH, or it is a ketone or an aldehyde with your double bonded oxygen, right? Now, your Cu group, your carbon with the double bonded oxygen, single bonded OH, we can't use because this one would have 2 oxygens, and the formula tells me I only have 1 oxygen present. I don't see a subscript of 2 on the formula, so I can't use this one. So these are the only 2 possible functional groups that I could use. So let's just play around and see if it'll work. If I use the one on the left, the carbon right here on the right-hand side of the molecule already has 3 bonds, so I could put a 1 there, a hydrogen there. That'd be 1, 2, 3, 4, 5, 6. Yep, that works. I've got the 3 carbons, I've got the 6 hydrogens, and I've got the 1 oxygen. Let's look at this one, the molecule on the right. Carbon on the left needs 3 hydrogens. That'd be 1, 2, 3, 4, 5, 6, 7, and that would be 8. So I can't use this one because if I use an OH group, an alcohol group, I cannot make the molecule stable with only 6 hydrogens. So this one is wrong. So the one on the left is correct. Let's name that. So I've got 3 carbons, single bonds in between, so that would be propane for my base chain. I see this functional group, and it's coming off of carbon 1. So guys, this is at the end of the molecule. It's on the first carbon, or the last, based on how you're viewing the molecule. So a double bonded oxygen on the first or the last is called an aldehyde, and you name it by changing the E at the end to Al. So this would be 1-propanal. Okay, let's see if we can draw another isomer. So I've got the 1-propanal. I'm going to kind of clean up my screen a little bit so we've got a little bit more room. We need to be able to draw another isomer of this compound. So I can still only use 3 carbons, 6 hydrogens, and 1 oxygen. If I do it correctly, it will have a completely different name. So remember, this one on the left was 1-propanal. I have a lot of students try and do this. But if you do that, you still have 3 bonds right there. Your carbon, the functional group would be closest to this carbon, so it would still be 1-propanal. So I can't use that one. That one's wrong. Okay, how about if I put the double bonded oxygen right here, then I would use 1, 2, 3, 4, 5, 6. I would have 6 hydrogens. That's correct. I'm not adding a hydrogen here, but I shouldn't because this carbon already has 4 bonds. So I've used the 3 carbons, the 6 hydrogens, the 1 oxygen. Now, if I name this one, my base chain is still propane. But now this is no longer an aldehyde, it's a ketone. So this would be propanone, and it would be 2-propanone. So do you see how we have completely different names? So when you have the same formula, but different names right here, same formula, different three-dimensional structures, different names, that means that you've drawn the isomer correctly. I'd like to do a little bit more practice with you. Let's take the compound C5H12. See if you can draw 2 or more isomers of this structure. So if I draw out 5 carbons, 6, 7, 8, 9, 10, 11, 12. So that's 1. And if I was to name that, that's my base chain. Base chain has 5, so this would be called pentane. Okay, can I draw it a different way? How about if I did 1, 2, 3, 4? And how about if I put a side chain right here? Hydrogens 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep, I've used 5 carbons, 12 hydrogens. Base chain, oops, sorry, let me switch colors. Base chain now has 4, so I would call this butane. And my side chain would be coming off of carbon 2, so I would call that 2-methyl-butane. Yep, that would work. Okay, I have some students try and draw another one and do this. Third isomer, do this. That would be incorrect for a third isomer because that is still the 2-methyl-butane. Now you're just numbering from this side. Okay, I'm just going to move these names over to give us just a little bit more work to continue. Should have sketched these over a little closer to this side, giving myself a little more room to work. Okay, it's just so we can remember the ones we've already done. Okay, so just to be clear, this and the one we just did before, where your side chain was right here, are identical to each other, and therefore those are not isomers of each other. How about if we did this? And then let's say I do one here, and I do one here. Okay, if you count up, I've used the correct number of carbons and hydrogens. Let's circle your longest base chain. Or you could have circled this. In both cases, you have 4. We would have a side chain right here. It would be coming off of carbon 2. You have 4 carbons in your base chain. So do you see how that is still 2-methyl-butane? So this one would be incorrect because it is not an isomer. It is not another possible isomer because we've already done that one. We've already done the 2-methyl-butane. Okay, so that one would be incorrect. How about if I drew this? So if I've used 5 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. Base chain has 3, so that would be propane. It's looking good because I have a different name for my base chain. I have a methyl group there and a methyl group there. They're both coming off of carbon 2. So I would call this 2, 2 dimethyl propane, meaning I have, let's break down this name one time. I have 2 methyl groups, one coming off of carbon 2 and the other one also coming off of carbon 2. So this is a third possible isomer. So I have drawn the 3 possible isomers for this structure. If you have drawn anything else, it's incorrect. If you study it for a minute, you'll see it will either be named pentane, 2-methylbutane, or 2,2-dimethylpropane. So there are 3 possible isomers of the compound C5H12. Okay, so you need to be able to, if I give you a formula, if I give you something like C2H6O, and I ask you to draw 2 isomers of that compound, you need to make sure you've got 2 structures that would have the same number of carbons, hydrogens, and oxygens, but that would have 2 completely different names. That's how you know you've done your isomers correctly. Okay, excellent job, ladies and gentlemen. As always, contact me if you have any questions. This is just the very tip of the iceberg with organic. If you've really loved this lesson, see me and I'll be happy to teach you even more. This can get really complicated really fast. You are just required to know the basics for me. But if I've piqued your interest, see me and I'll teach you even more. Have a great day.